This video is for those who are new to the gradient descent algorithm and want some visuals to get an intuitive understanding of how to visualize the algorithm in their minds. I will only guide you to think, but other than that, you have to think on your own about these graphs and understand the idea of gradient descent. We have just one weight to learn for this function. I'm using a single weight because it's easier to visualize and explain the concept of gradient descent. First, let's focus on the first graph, which plots the relationship between y hat and the input x. We have some data, and our goal is to learn the linear pattern within it for a simple linear regression task. This graph shows the relationship between the input and the predictions that we aim to learn. Now, if we change the input x, we will get different values of y hat. Our goal is to adjust the function so that we get our desired output y for each input. In this case, our goal is that when we feed the input x from our data points, we should get the corresponding y value for each data point. You can see we have a weight value initialized to 1.0. X is the input we feed to our model, and for now, its value is 1. Using this input x and the weight value, we get the output y hat. You can see this represented in the function above. You can also see this in the first function, which shows the relationship between the input x and the output y hat. Y is the actual value we want to predict for the input x. We only have one y value, which is fixed for each input. Now let's understand this second graph, which is plotted between the loss value and input x. While looking at the second graph, just observe how changing x affects the overall loss. Remember, we don't change the input in the training process. We get x from the dataset, and also for each x we have a separate label. But for some tasks, we have the same labels for multiple inputs. If you look at this actual value, it is 1 for input x. Because the output y hat and the actual y value are the same for the given x value, we have a loss of 0, which you can see in the second graph. Let's say we have an input value of 2 and we want to map it to -1. So for that, we change our label to -1. To get this prediction value of -1 for the given input. You know that to get the minimum loss value, these two values should be the same for mean squared error to achieve a minimum loss of 0. But because these values are not the same, we have some loss value and our goal is to reduce this value to 0 by changing the weight w. Now look at the fifth graph, which shows the relationship between y, which is the label, and the loss function. But because this is the label, and we have a fixed label for each input, we do not change the label. But there is a way to change this function to get minimum loss without actually changing the value of y. We move to the next function. Here we can increase or decrease the y hat value to increase or decrease the loss value, which is our main objective. This will also decrease the loss in the previous function. I suggest you pause the video here and think about the relationship between these two functions. How changing one function's x-coordinate affects the other function's y-coordinate. If we look at the last graph again, here we cannot change the y hat value directly because it is dependent on the weight and input. We can see the input x is always fixed in the dataset. So we change the weight. You can see the impact of weight w on both functions. Changing the weight changes the output y hat and impacts the loss. You can see both these graphs are similar. This is because we have input x set to 1. So the values of weight w and output y hat are the same. To understand better, let's change its value. Let's set the value of input x to 2.0 to understand both graphs better. Both these graphs are the same, it's just that the weight is doubled using input x, so the lower graph is more expanded. We want to change the value of y hat so that it matches the actual value of y. You can see this relationship in this graph, which will tell you the value of weight w that will give us an output of -1. But here we are looking at it with the help of a graph, right? If we move one step forward, we get this loss using this equation. This will convert the distance between y and y hat into a loss value, and decreasing it reduces the distance between y and y hat, resulting in the same predicted and output values for the given input. All this is plotted in this third graph. Usually in regression tasks, we have a minimum value of loss for all the inputs. But if you look at the second graph, you can see for different x values we have high loss. Only at one point we have a low loss value in the graph. It's because we have the same y value for all the inputs. But for each input, if we have its own label, this graph will look something like this. It's because now we are not just changing the input x, but we are also changing the label, which cancels out the effects on the loss function. But what if we want to map all the output to a single value? We do this in classification tasks for each class. This is not possible with linear functions, but there is one exception to it. For this, let's change the label to 0. We also set the weight to 0. Now if we look at the second graph, it will give low values for the given inputs. This first function is what we want to approximate. This second function is usually irrelevant and we don't usually need this. Third function is used to calculate the gradient for each weight to apply gradient descent algorithm. These two graphs will have a minimum where y and y hat will be the same, but we usually change y hat because we learn this from the training process. If you look at y, it stays the same, but we get minimum loss in that function also because of the change in y hat. Overall, the voiceover was to guide you to think about these graphs. Now try to understand each graph and figure out why and which graph is important and which is not important.